So, to be very upfront here, um, I am not as prepared as I would like to be today. I did this lab last semester and I've pulled it up and it is working and I've glanced through it. I don't know how many things have been changed since last semester, but as I'm looking at the code now, the way I would do it now is not the way I did it last semester. And so, I know that a lot of times y'all base your code off what I suggest, and I might suggest that you do something a little bit different from what I have done here, but I'll explain what I mean by that. Um, so, uh, let's talk a little bit about the lab and what it is that you're going to be doing. So, I am going to stop the share so that you can see the base. Oh, I think I need to turn off my background. Let's see. That, by the way, is Yellowstone. Went there with my two brothers not that long ago. Okay, so here's the basis board, and what you're going to be, you know that, what you're going to be doing is programming it to make the LED lights have a certain pattern. So I'm going to go ahead and send the program to the board. Open hardware manager, open target, open new target, next. I know y'all can't see what I'm doing. All I'm doing right now is just programming the board with the program that's already written, just so y'all can see what's going on, what your goal is going to be. Okay, so now, all right, so here's the board, and I don't remember if this is part of the program, if it's something I added. So it doesn't start until I turn that first switch. I don't remember if that's part of it or not. And you can see that I have a mistake there. It's skipping one of the lights as it's going through, or maybe that was part of the assignment. I don't remember. But the idea is you're going to be programming the board to have a certain pattern of display of lights, and it's sequential. So it does, each time it's doing something, adding something to it, and then it repeats itself. And so that's going to be your idea of what it is that you're going to be doing in this particular lab. All right, now let's look at some of the details. Okay, so the first thing that you have to do is build a 5-bit counter similar to the one shown in figure 553 of the text. Let this base counter with load be a module called alpha beta counter. Its clock will have to be generated separately as explained in section 3. In building a modulo x counter, detect and verilog a count of x minus 1 in the base counter, then load 0 at the next clock cycle. Okay, so let's take a look at figure 533 in the text. I don't remember where I got this, if y'all are wondering. Um, okay, so 533. That doesn't seem right. Did I misread it? What did it say? 553. 553. Okay, so this is a 4-bit up counter with a parallel load, and we're gonna use parts of this, but we're not gonna use all of it because we don't need all of it. So on this one, it uses an extra thing that we don't need, which is the reset in. So the reset in is a way to reset asynchronously the counter. So you can just, at any point, you can send it a signal to say reset. And we are actually not going to use that. So we're not going to use the reset in part. So that part we can leave out. We will, you do need to have an input of some sort of clock, and we'll get to what that clock is going to be. And so, like I said, we're not going to have the reset in. If you have load, if L, then you're going to load a certain value. So that is if you want your clock to count like this. So let's say you wanted your clock to count 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 5, 6. Okay, so what you would do there, you build a counter, and all a counter does is go in order 0, 1, 2, 3, 4, up to however many bits you have it set. Say you have it set at, you've got 4 bits. 4 bits would be 16, which would go from 0 to 15. And then so you go 0 to 15, the next one would be 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 0, 1, 2, 3. But if you wanted to have a different pattern, you would load 5. So in this case, I would load 5.
Were you meaning to share your screen?
Am I not sharing my screen?
No.
No? Okay, well, you know what? I did mean to share my screen, and I'm sorry I've been talking this whole time without sharing it. Thank you for saying something. Okay. Oh, okay, yeah, so y'all didn't see any of that. All right. Okay. Please interrupt me sooner. I have been not getting much sleep lately, so let's see. Okay, so let me go back.
And we are
All
recording,
right.
correct?
I am recording, yes. So I get to record like all of my mistakes, yes. So so I'm recording two ways. One, I'm recording with Zoom, so you're getting whatever you'd see on Zoom, and then I'm also recording my computer screen. So hopefully one or the other will have what you need.
Got it.
Yeah. Okay. And let me just check. Do I have anything in chat? And as usual, I can't get to it. There we go. It doesn't look like there is. Okay. All right. So this is figure 533 from the textbook. So what this is a 4-bit counter. The reason it's 4-bit is if you look at Q here, Q has bits 0 to 3, so that's 4 bits. And it's saying that if E, so E appears to be, must be an enable. So if E, so if enable, whenever it gets to a positive edge of a clock, it's adding 1 to Q. If it's L, L means load. If it's load, then it loads a particular value. And we're not going to use the reset in, so we don't need to worry about that. Now let me go back to the reason why you might want to load, which is what I was describing to myself without sharing my screen. So I'm going to make this a 3-bit counter just because then I won't have as many numbers. So if I have a 3-bit counter, it would go 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3. Okay, so that's how it would go on its own. But let's say instead I wanted to have the pattern 3, 4, 5, 6, 3, 4, 5, 6. Then what I want my code to do is I want it to check and to see what value Q is, and if Q equals 6, then I'm going to want to, this is not the actual code, but it'd be some code that would make it load 3 and then start counting again. And so that means that if it's counting, let's say it's at 5, 5, 6, it gets to 6, Q equals 6, so it's going to load 3 and then count 4, 5, 6. It got to 6, it's going to load 3, 4, 5, 6. So that is how you can have your counter have different patterns. So if we look at the code in the book, right here, it has the way it says to load is if L. So if L equals 1, it's going to load, and it's going to load this value R. If L does not equal 1, then it makes Q equal to Q plus 1, and that's the actual counter. So we're going to modify this a little bit to meet our needs. First of all, we need a 5-bit counter because when we look at our instructions, we need to have a modulo 7 counter. So a modulo 7 counter will go from 0 to 16. So you might think, oh, 16, well 16 is 2 to the 4th, so I only need a 4-bit counter, except that we're including 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So those are the binary numbers 0, 0, 0, 0 to 0, 1, 1, 1, 1 right there. And then to get to 16, I need 1, 0, 0, 0, 0. So I need to have 5 bits in order to go from 0 to 16. If I just wanted to go 0 to 15, I'd only need 4, but to go 0 to 16, I need 5. Okay, so I need a 5-bit counter. Let's see, what else do I need? So it needs to count from 0 to 17, and we're going to put that 17 in our code as a parameter. So right here it says parameter equals 17. So I could change that if I wanted to. For instance, I told y'all that I just loaded the code that I wrote last semester to see if it worked, and I was looking at it. It's like, well, it seems to be working, but it's only going up to 8. So I know it's supposed to go to 16, and then I just looked and I had changed the value. So actually, I don't think in my code I have the parameter. You might need to add that to yours. Okay, so we need the modulo counter, so let's look at that. We'll come back and get the clock. Okay, so this takes the code from the textbook and takes out parts that we're not going to need, and then changes the parts that we are going to need. And you can modify this some. I don't remember if this is, as we go through it, I'll be able to tell whether it has everything we need or not. Okay, so this is a 5-bit counter. We have as an input R. R would be whatever it is that you want to load, depending on what pattern you're trying to get. You're going to have your clock. Now this clock is your system clock. You're going to have to make another clock, and we'll talk about that later when we get to that. So this is your system clock. You have an E. I'm assuming the E is for enable. You have the L, which is telling you if it's time to load. L would be 1. And you have Q. Q is your output. Q is the thing that you're actually counting. So that would be the actual number, the 1, 2, 3, 4, 5, 6, 7. You'll have an input that is R, that is 5 bits. That would be the number that you load. So for instance, if we had to have a count sequence, that would be 8, 9, 10, 11, 8, 9, 10, 11. Then in that instance, R, you would have R equal to 8, because that would be what you would want to load when it comes time to load. And then you have your clock and enable and L. And enable and L are probably, enable is a switch. On mine, I have it as the switch that's farthest to the left. And I don't remember what L is. We'll find out when we get there. And then Q, that's your output. That's what's going to go to your module that is actually turning on the LEDs, because you're going to base which LEDs are on based on the value of Q. Then this is the part where I said it was good news if you understood the lab from last week, because we need to have another clock that we make, and we're going to call that clock div again. It's going to be based on the same code as it was last week, and we have to get a new clock signal from this new clock, and I called that capital CLOCK, and I made that a wire. And so what this is doing is I have this other clock, so I have clock div that ticks more slowly than the system clock. And it's as slow as you saw those lights move when I did the demo. So 1, 2, 3, 4, or 0, 1, 0, 1, 0, 1, 0, 1. And so this counter is going to count on the tick of that slower clock. You don't want it to count on the tick of the system clock, because then it would do 100,000 per second, and that's not very useful. Okay, and then so here's how this counter works. It's pretty much the same as the one from the book, except we took out the reset in. So if you want to load, then you would say, well, let's make Q equal to R, whatever you send it for R. Else, if it's not time to load, if it's enable, then you would add 1 to Q. So if the enable switch is on, so if it is supposed to be counting, then when you get to the positive edge of the clock, you add 1 to it. Otherwise, you just keep Q as it is. Now, okay, here's an example of where I would do things differently now compared to what I did before. So notice here, I only have my clock does not have a time to tell it to start over unless I'm loading something. I'm sorry, my counter. So I have my parameter for when to switch. Okay, so we had modulo 17. So we're supposed to count from 0, 1, 2, up to 16, and then back to 0. This one is going to count from wherever you load all the way up to 31, and then back to 0, and then up to 31. And if you wanted to stop it earlier, you would do that in the other module. And I think we need to change that here. So I think what you would want to add is here. So we would want to have, so let's go back to this. So you'll want to tell it when you want it to stop. So that I'm putting that in as a parameter. it changed my parentheses E to a euro. I think he said modulo 17. Okay, so let's see, does this seem like it would work? So if it's enabled, then we would add 1 to Q. But if Q has gotten to be as big as 17, then we want it to return to 0. Yep, so I think that would do it. So this would be, not 17, X. That's why we put the parameter in. And then if you needed to change this value, you would change it up here at the parameter. So parameter X equals 17. So if you needed to change that. I'm going to take a peek and look at the book code. It's not in here. All right. So depending on time, if there's time before the session's over, we can try it out and see if it works. Okay. So that would build the counter, and that puts the modulo part in this module and not in the main module where I had it before. So before I go on, are there questions on this part? There's chat. So this is the modulo M counter. So this is the same idea as what we had here, done a little bit more efficiently than what I had. So if you look here, so the parameter is M, so it says if Q equals M minus 1. What I did, so the difference between this one and what I did is I added first, and then if I had gotten to that high value, then I went back to 0. This one, it first checks to see if it's, so like if it's modulo 17, it checks to see if it's 16 first, and if it is, then it goes back to 0, and if it's not, then it adds 1. So This way is a little bit more efficient, but again, we're not using the reset in, so you don't have to have that one in there.
Thank you for clarifying.
Oh, you're welcome. Any other? Did that explain it?
Yes. Yeah, just little differences between the two, really.
Yeah, yeah. They should both work. Although I'm terrible with making syntax errors. But it's the same idea. It's just this one checks before you add, and mine adds and then checks. So that's why it has m-1 and mine has x. All right. With the parameter, would you need to state two numbers? Um, are you saying that because you're asking about a beginning and an ending value? Okay, so the answer to that is no, but only because what the directions say are to build a modulo. So let's go back and look at the directions. So the directions say to build a modulo 17 counter. And so a modulo 17 counter means that you intend for it to stop at 17, but to start at 0. So it should be able to start at 0, 0, 1, 2, 3, 4, 5, and so forth. The second number that you're talking about, that would be the load. That would be this R right here. And that's not a parameter. That would be something that you send it from another program. That could be a way of building the counter. It's not that having the two parameters would be wrong, because you might want to have a counter with a stop value and an end value both as parameters. It's just not what this particular lab told you to do. So in this particular lab, if your start value would be R that you would send to it from another module, but your end value is you want it. You might also end it somewhere else that you would send to it from the other program, but this one automatically ends at 16. Okay, other questions? Okay, I think I want to go next to the clock before we look at the combinational logic. Okay, so yeah. All right, so let's look at the clock. So you did a clock in your last lab, so you should already have this. And there's not going to be much that you need to change from it. So it's clock div. And we'll talk about the things to change. Okay, so he says in your directions to produce create a module that produces a clock around 5 hertz. Now, I think I remember, so 5 hertz means 5 per second, because a hertz is a per second. And I think I remember, and I could be wrong, you can go and look, in the last lab, what the speed is of the system clock. And I think we said it was about 100 megahertz. So if I want to go from 100 megahertz, so that's 100 times 10 to the 6 hertz. I want to go from 100 megahertz to 5 hertz. Then I want that I want my clock to toggle for every 5 hertz, but the system clock toggles every 100 million hertz. So to make it toggle every 5 hertz, I'll take 100 million and divide it by 5, and that got me whatever this number is, 20 million. So, oh, of course, 100 divided by 5 is 20. So 20 million. So I get 20 million. And so if the system clock toggles 100 million times per second, and I only want to toggle 5 times per second, then that means I want my clock to toggle one time every 20 million times the system clock toggles. So every 20 million times the system clock toggles, I want mine to toggle once. And that's the number that I have in here as my parameter. Now you may need to play with this to get yours to go at the right speed, whatever speed that you want. So this would be the number that you're going to put in here to change that. Now, one thing you need to be careful about is your count variable here. This count is the number that's counting every time the system clock goes. And so you need count to be big enough to go all the way up to 20 million. And so you need to figure out to what power would you need to get a number, the smallest number that's greater than or equal to 20 million. And it looks like I had 25 there. Let's see what that is. I know that OneNote has a calculator in it. I don't know where it is. So 2 to the 25th is 33 million. 2 to the 24th is 16 million. So 2 to the 25th, that's what I would need to have if I needed my number. Well, this is going from 0 to 25, so that means it actually has 26 bits in there. So this gets me a little bit extra. So this gets me, so I could go up even farther than 20 million. I could go up all the way to 67 million if I needed to. So that's, you would need to change the size of that. But other than that, this is going to be the same code that you used for your clock div in the last lab. Okay. All right. So Raylan, you're good now?
You guys
Yes.
see?
Okay. All right. Okay, so any questions on the clock before we go on to the combinational logic? All right. So again, this is not mine is not ideal. So I want to make sure that y'all know that, and that you play around with your own and make it better. Well, first, let's look and see what it is you're supposed to do, because make sure I'm even doing the right thing. Okay. Okay, so you are supposed to write a module called Alpha Beta Combinatorial. You can see I wasn't thinking about it right when I wrote it, because I was, thinking of it as the counter, but the counter was supposed to be another module. So, we've talked about the counter. We've made the 5-bit counter. Detect and Verilog a count of x minus 1 in the base counter, then load 0 at the next clock cycle. Well, okay, that is how the example was. That was in the chat, and mine detected a count of x instead of a count of x minus 1. And here, well, it does detect that. So it says this can be done simply by checking if q is x. And so that's what I had in my head, because right here it says check if q is x. So that's what I did. And then set the next state equal to 0. But you can also detect if q is x minus 1 depending on when you check that. And then if we want the lights to be lit according to a count from 0 to 16, then this would be the pattern that you would have on each count. So at the count of 0, none of them would be on, and then 1, the first one, and then 2, the second one, and so forth. And this is telling you convert the count to 16 output signals that are shown in the LED. So for example, if you define a vectored signal as output 0 to 15V, then you can set the constraint VI to the ith LED. So I think what I did was probably in my typical lazy fashion, I probably looked here to see what it was already called in the constraints, and it was LED. I think that's what it is. Let's see. Yeah, in the constraints, the variable name is LED, and I said, okay, well, I'm just going to call mine LED, and then that way I didn't have to rename the constraints. And so, similarly to how we set the 7-segment display, you'll have a 16-bit number that you'll have zeros for the ones that you want to have unlit, and a 1 for the ones that you want to have lit. And so you can just set it up like that. Okay, so let's take a look at what all we have here. So output reg R. Why is that an output? Okay, So this is different from, okay, so this is, the way I have this set is, if you recall, I did not have my counter set to go back to 0, and when it got to the end. And so instead, I had that here, I had it R. I said, if we got to 16 here, then load 0 through R. But you can still use this where I have output reg 40R in case you wanted to load a different value. So let's say we now have the counter set to start at, to when it gets to 16 to start back counting over again. We could change this to, in case we wanted to have it, let's see, if we didn't want it to start at 0, so if we wanted it to start at like 6, then we would change this to 0, 0, 1, 1, 0. And that would have it start at 6. And let's say we wanted it to go from 6 to 11, then we would change this parameter to 11. I think 11, it might be 12, you'd have to try it out and see, it might be off by 1. And so that's, we kind of have double duty here. You can use this both ways to set your beginning and ending value, because your counter also has the load function. Otherwise, if Q does not equal X, then your load is going to be 0. You don't want it to load. So if you use both this and the modifications to the counter, then you have it, it'll doubly reset. It's not really going to doubly reset, but it would make, it has it in here twice to where it would go back to 0. Okay, other than that, what we have here is what you want the LED string to be based on Q. And so, and this may change in the lab if you're supposed to have different patterns. Let's see what the lab says to do. So pattern 2, so pattern 1 is 0 to 16. You wouldn't have to change anything. Pattern 2 is 0 to 7. So all you would have to do there is change either in the combinational code or in the counter code to make x equal to 7. Except you're going to have a different pattern, and so you're going to change what your patterns are for 0, 1 through 7 just based on this picture here. And pattern 3 just goes from 0 to 4. And then if you have time, do a different pattern. So all of that should be pretty easy. You do want to include a default. Notice that if I wanted 16 zeros, I can just do 16 here and be 0. It knows those should all be zeros. Okay, any questions? Check my chat.
So are we setting the R, like the R value in the counter, or are we setting that in the second part, the combination?
You can do it either way, and that's where I'm just being confusing to y'all, because the way I did it last semester was I set it in the combinational part, and the way I think you're supposed to do it is to set it in the counter part. And I currently, with what I've told y'all, I have it where you could do it in either one. So I have, so I'll show y'all. So right here, we added. No, that's not it. We did. That's not it. We did. Why don't I instead, well, no, I've already started this way. Oh, don't let me forget to go over the top module with y'all. Oh, I didn't put X in.
If we're setting q equal to 0 whenever it is equal to x, or yeah, would we even need to have r and l? Because we're just loading 0 whenever it reaches the x.
You don't? No, that's what I'm saying. I've got redundant code here. And well, actually, no. You do need the R because that's if you want to. This will be if you so the equaling x tells it where to start. But oh wait, I have this in the wrong place. Hold, this is in the wrong place. So the L is just for loading. So the R, it tells it where to start. The equaling X tells it that it's time to stop. But this is not right. Hold on. If load, no. If it's loading, all I want to do and then this is where I want this. Actually, I do want that.
Just to make sure and be correct. So for the R's, those are what's gonna be, let's see.
Okay.
The R's are going to be for the let's see.
Yeah, I'll
For the
explain.
okay, because I was just trying to piece it together because like you have to have different names. I mean not names, different like bit numbers for R's, correct?
Yeah. Okay, so let me change this. So, uh, So I will explain. Let me see if this compiles first, and then I'll explain. While it's compiling, let me come over here. This is, now you do not have to do it this way. This is just how I did it. And like I said at the beginning, it's a little bit messy because, you know, last semester when I did it, I'm not sure it was efficient. And so we have a modulo counter that's based on this code from the book. And the code from the book includes an R that you can load, but it also is a modulo counter which uses a parameter X to tell you when to stop. And so your counter does two things. So one, well, it does several things. So one, if you're supposed to load, so if load, then load R, which I had changed my name for that to start num to give it a more descriptive variable. So if you have the load, then you're telling it, then I want you to start at this particular number, like I want you to start at 5 instead of 0. If you get all the way to X, and this is a modulo X counter, modulo X, if you get all the way to X, go back to 0. Otherwise, you would say every time you count, you would want to add 1 to Q. So your value is going to go 0, 1, 2, 3, 4, 5, 6 to wherever you told X, whatever you said X would be. So maybe you said X was 8. And then if you get to 8, then you go back to 0, 1, 2, 3. But on the other hand, if you tell it, and no, I want you to load a value, then it's just going to go straight to that value that you load. So if you tell it you want it to load 6, then it's going to start at 6. It'll go to 6 and go 6, 7, 8, and then back to 0, 1, 2, 3, 4, 5, 6, and so forth. So that's the difference. Let's see if I programmed it correctly. Shut down for some reason. Okay. Still compiling. Okay. So I'm just waiting for it to compile. All right. So did that kind of answer your question about the R and the X?
Yeah, because I was a bit confused on, like, what does R mean? I know what L means since you mentioned it about loading. And I was like, okay, so what does R would be considered as? So what would it be is used for?
Yeah. So my computer keeps disconnecting the board. Don't know why. Yeah, so the R is the load value. I don't know that you need it on this one because with the patterns, so you could probably leave out all of the R stuff because all of your patterns are starting at 0. And so you wouldn't need to ever load another value. But I know in the homework, he has times that you have to start at places other than 0, so you would need to know how to do that. Now, it does here, Right. So the modulo counter always goes back to 0 when you get to the place where you want to end. This one, within the combinational logic, it says if you get to the ending value, which is x, that's when you give it the new starting value, and it loads that starting value. And hopefully you'll get done compiling soon. Running root design. Yay.
Nice.
Thank you. Thank you. Except for obviously I have one of my bits wrong somewhere that I have my skipped one in there. But what this means, and I don't really have anything else to add, but I'm going to show you if you want to stick around and see what happens if I change the start number to a different value like 6. We see what that does. So I don't know how long it'll take it to do this. But that's oh, I was going to show you the top module. So while it's compiling, I'll show you all the top module. Okay, so all the top module does is it puts together the different modules that you have written. And so your only inputs and
You're not screen
outputs.
sharing right now.
Thank you, thank you, thank you, thank you. I didn't get that far this time, so let me get to it. Okay, so on the top module, we would have just your clock and the enable. Oh, and I'll talk about the constraints too. The enable and the LED. Your input, this is your system clock. Your input E, that's going to be a switch. And then because I used it, I have this, what was R, it's now start num. You could do without that one, because you could just have your counter just go to 0 and you can completely leave out that R and start num altogether. The wire L is for loading a new value. And if you're counting on your counter doing all of the work, you wouldn't necessarily even need to load either. So this just lets you load from your combinational circuit. If you wanted to do that all from your counter, you could do that as well. And then your output is your LED. And then you need to instantiate, this is supposed to be combinational something or another. And then you'd have your inputs from that. So that's all your top module does. It just puts those things together. And then for the constraints, you would have so for your constraints, you're going to have the clock. Now make sure you have the clock, the one that he has written for you in, he might not have a copy of it in this lab. You might need to go back to the previous lab to get it. So yeah, it looks like you have to go back to the previous lab to get it. But make sure you get the correct constraint for that clock. So you want the clock from that lab. And then you'll need one pin, one switch to be your enable. So on mine, it's the switch farthest to the left. If I turn it off, it doesn't do anything. If I turn it on, it does its count sequence. And then you need your LEDs. Like I said, I just called mine LED to save having to rename things. Okay, any questions?
I have a question. Could you possibly go back to your counter
Yep.
counter, please? Because I was getting a bit lost and kind of sidetracked with what you had, because like I have two different ones and I was trying to make sure mine's follow along what you had.
Okay, so this is what I currently have. And again, I really encourage y'all to not just strictly do exactly what I do, because A, because you'll learn better, and B, because I kind of have like redundant things in here twice. But my counter has start num, which in the book code, if we look at the book code, they called that R. Or they didn't have it at all. Never mind. I thought it was there. So it's not there. Okay. All right. So start num. So that would be a loading value. You will need that in some of your homework problems, even if you don't use it here. So you could leave the start num out altogether, or R. You can leave that out. Clock, you have to have that. E, you need to have that. L, you don't need to have that if you're assuming you're always going to start counting at 0. So if you always start counting at 0, every time it gives me less options of what to do with the bit stream generation. I want to check this real quick and then I'll come back and talk about counter again. So hold on. It didn't work. Okay. Maybe it's not actually programming it. Well, it didn't work, so it's still starting at 0. So I'll have to play with that and see what's going on. Okay, but what it's supposed to do is it has this value start num that it gets from somewhere. It has a clock, it has enable, and it has load. And then it has its output, which is Q. It has a wire, which is clock, which connects the the clock div to your counter. It has a parameter that tells it where to stop counting. And then you have it's actually doing its counting on the positive edge of your clock div. So right here, whatever you name this variable, that's what you want to have there. If L, so if L is 1, this is where it's supposed to load the starting value. But if you're doing without L and the start num, then you just wouldn't have this at all. And instead you would just start with if E. And so if enable means it is supposed to count. If enable, you add 1 to Q. If Q has gotten up to your top value, you set Q back to 0. And else, so this is else, so this is if it's not enabled. If it's not enabled, you keep Q as it is. And that's the counter. So
Okay, thank you. Because it was a lot. I know we had a lot for that top part, and I was trying to make sure that I had the clock for it.
okay, well the top module is just this part right here.
Mm-hmm.
That's not the counter. The top module is just putting everything together.
Oh, not the top module. I'm talking about the counter to make sure I had the clock
Oh, the
for it.
counter. Okay, yeah.
Yeah, because I was like, so I was trying to make sure I had everything with the counter because it was like I had some stuff like a bit duplicated from like the other stuff that I previously wrote. So I was trying to
Right.
make sure it wasn't all the same thing.
I see. Yep. Oh, I see my mistake. Right here. That ought to fix it. But I have to go, so I'm not going to keep y'all around any longer. But I think that is why it did not start at the starting values, because I did not change that value in my chat. Are you planning to post this recording? I'm planning on it, yes. So, should be available for y'all to see. Other questions? You're welcome. All right. I will see y'all on Wednesday when... Do y'all have homework due Thursday?
Yes.
Yes.
Okay, so I will see y'all on Wednesday to help y'all figure out what you need to figure out for your homework, except not to actually do the homework problems, but to give you the information that you need for doing the homework. All right. Okay, see y'all Wednesday. Bye.
Thank you.
Thank you.
Bye-bye.